at close to that time. But, and they actually had a software piece that was built into one of these stations, but also wasn't a particularly good piece of software. And so if you would go look out the window and go, okay, take a picture of Mount Everest, and you're looking down at that, you're just going like, well, good luck knowing which of those is Everest, which of those is K2, and by the way, it's moving by pretty fast. And so people, the astronauts on board would generally miss targets. And you can only really have, one target every 5 minutes because you need to get a piece of paper out again and orient it and figure out your strategy for trying to know when it came by the window. And so what I helped develop is this thing called Windows on Earth, which was a scrolling window that exactly matched what was out the window. So it's kind of like Google Earth scrolling in synchronization to what's out the window, with little red circles around all the targets, the circle size being the lens focal length recommendation, and a scroll countdown timer of this is 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, so you can actually see things that are outside of your view, but get a real sense of their countdown as it's coming to you. And on the bottom is even a couple of orbits of time, just so you can see further ahead. And so this let me take 10 times as many photographs, far more reliably than the professional astronauts who were sitting next to me. But what was interesting is before I launched, we all know what the targets are. We're given this list of targets. So I actually took their targets and imported them into my tool. So I actually had all of their targets with me, and they were tagged as to whose target it was and what the name of the target was. And so what happened, though, is the professionals would come over when their targets came up and go, hey, Richard, I know you've been using this window, but, hey, I'm the professional here. I take, precedence. Sorry, but I need to kick you out of the window. And by the way, can we use your tool? and so that left me to sit back here taking pictures of them using my tool, so you can see the Windows on Earth that are running there, that they're all using to glance at to take their shots. So anyway, I thought it was kind of fun. And one of the other things I did was to answer kid questions, in this case for a newspaper in the UK. And I actually thought that, kids ask the darndest things is, a interesting truism, because I think some of the things they ask are either insightful and or really don't have super obvious answers. And so now I'm going to test y'all's knowledge on space to see if you're as smart as the 5th graders that are asking these questions. And so the first question is it hot or cold in space? Who thinks they know? Yes. Cold. We have one vote for cold. Both. We have one vote for both. 2 votes for both. 2 votes for cold. You're orbiting the Earth. Okay, so interestingly, the both is actually the correct answer. Unlike the movies where it's always cold. And of course, it's also interesting that the definition of temperature is the rate of vibration of a molecule, and of course, space is a vacuum, and so it really has no temperature. But a kid asking the question is really saying, well, I feel hot or will I feel cold if I'm in space? And the answer is still, it completely depends. If you are in the sunlight, the sun heats you up, and the vacuum of space around you is like an insulating vacuum bottle for thermos. And so you will heat up until you cook, literally would die of being cooked alive. On the other hand, if you're in the shadow of the Earth or in the shadow of the space station doing some repairs, you will slowly radiate heat away through infrared radiation, and you'll get colder and colder and colder and colder and colder until you froze to death. And so one of the big backpack a lot of people wear in spacewalks is the majority of it, other than oxygen supply, is this big air conditioner and heater with this big lever to shift back and forth between the two that runs hot or cold water through a suit that you're wearing. Okay, number 2, here you go. This is a more interesting one. So let's suppose one of the kids asked, about what would happen if you strike a match in space. And so we're going to perform this experiment twice. The first version of this experiment is, let's suppose we're out on a spacewalk, we're in a spacesuit, but we have a box of wooden safety matches that is not in the spacesuit. It is exposed to the vacuum of space. And I slide the drawer open, and matchsticks begin to float away into space. I grab one before it floats away, and I strike the tip of it on the side of the matchbox. What happens? Sparks. Won't light because of no oxygen?
Aren't they magnesium when it creates oxygen?
You think that the tip, we think of light because of the tip. Any other answers? You are correct. But, so the tip of a match, the reason why it flares is because the solid that's in there, what are the three things required for heat, for a fire? Oxygen, fuel, and heat. And so you're creating the heat by striking it. The matchstick is fuel. There's also fuel in the tip, but there's also oxidizer in the tip. So when you strike the match in the vacuum of space, the tip will flare, but when you get down to the wood, it'll go out because there's no oxygen. Right? Fair enough? Okay, now let's repeat this experiment. Now we're inside. We're at the Garriott I was just showing you a picture of. And we're here breathing normally. It's a 1 atmosphere environment. It's the normal ratio of oxygen. It's not pure oxygen. I take the same box, but now with my bare fingers, I slide the drawer out, sticks begin to float away, grab a stick that's floating away, strike it on the side of the box. What happens? Explodes. Anything else? It's not pure oxygen. It's regular atmospheric pressure and mix inside the spaceship. If it was a pure oxygen environment, it'd be very dangerous.
Yes. The Russians probably kill you because it's bad luck.
Probably that would probably be true. So who had an answer? Does anybody have an answer?
I say it lights normally.
Lights normally. So what happens after the tip burns? Does the wood burn?
Yes.
Okay. So tip burns, wood burns. Tip burns, wood burns. As it turns out, it will do the exact same thing it did in the vacuum of space, but for a slightly different reason. So the tip will burn for the same reason. It's got oxygen, it's got fuel, you just created heat. When you get to the wood, your instinct would be that should keep burning because we're here breathing and there's oxygen around, and so the wood should be able to continue to burn. Except on Earth, when you strike a match on Earth, the hot, spent fuel and wasted fuel and carbon dioxide is warm, and so it rises away from it, which draws in fresh air behind it. And in space, there's no convection currents. The same thing with those crystals. And with no convection currents, you actually burn up the oxygen right around the stick, and it puts itself out. And so it actually will go out basically immediately. If you were to move the stick, that would keep it lit. You could do that. And what's interesting about that is when the fire alarms go off on board the ISS, which actually went off one time when I was on board, the first thing that happens when the fire alarm goes off other than a buzzer is it shuts down all the fans because that will put out the fire. So, and when until a fire alarm, there's huge fans all over the place because when you're sleeping, for example, at night, if there's not forced air blowing past your face, you'll breathe in and out the same pocket of air and die. And so, keeping air circulation across your face is actually important, really important. Anyway, so that's some fun. I also made some art in space in homage to my mom. What's interesting too about space is something called the overview effect, and this is what I think is kind of the most impactful part of the whole trip, is just looking out the window back at the Earth. And when you're up there, you're only about 250 miles up, and you can see the kind of curvature of the Earth you can see there. But you're not like on the moon and seeing the little blue marble. You're only, you're pretty close still to the surface of the Earth. In fact, when you look straight down, it doesn't look that dissimilar to looking out the window of an airplane. I mean, you're 20 times or so higher, but only 20 times higher. But you can still see airplane contrails and the same kind of clouds you see out the window of an airplane. It's further away, but not profoundly further away. And in fact, if you look down at a place you can see the Golden Gate Bridge and the Oakland Bay Bridge and Alcatraz and the ship there, the little V-shaped wakes behind the ship as it goes out. And it's interesting to see the silt plumes of the water flowing out of all these river mouths and basins. And that's a little ahead of time. I'm sure we'll come back to that. But when you look horizontally, it's interesting also that you can see really how thin the atmosphere is. In fact, if you go up to the height of the clouds, we all see from looking up from the ground and sometimes fly over in an airplane. It's only maybe 10 times higher than that before there's so few molecules of air that there's not enough molecules to refract the sunlight. So it gets thin quick. Once you're above the clouds, it gets thin really quick. And the space station is only a little bit up into that blackness. I mean, you're not really very far above the thin atmosphere. But as you look out the window, it feels like there's this fire hose of truth kind of about how the systems of the Earth work. You know, you notice a lot about weather and how, like, over the Pacific, you'll get these very laminar, big shapes that are undisturbed because the temperature is all of one kind of temperature. There's no land masses to cause chaos. Chaos bad. Until you go over the Atlantic, in which case chaos good. And because over the Atlantic, you have the shallower waters that are warmer, that are creating more energy, and different temperatures and land masses and islands and things, which tends to cause more chaotic behavior. When you look out at land, you can kind of see how the physical shape of the Earth has been changed by everything from tectonic plate movement. You can see the fault lines of the Earth in a kind of cool new way, because you can kind of watch them all and how they connect together, you know, all around the Earth in a really just kind of cool process. You get to see how water is just washing material off the continents and back out into the oceans. You can see how even wind is creating this erosion that you would never perceive these patterns from the ground. You know, you wouldn't see that those kind of lines going across it, because each one of those lines that you see there is, you know, probably 500 miles apart, and so it's a rhythm that you could only really detect from space. And then after going around the Earth, you know, some dozens of times, in fact, whoops, I mean that one slides out of order too, so I'll come back to that. But you know, as you go over mountain ranges, you begin to notice how there's roads and dams basically all over the whole Earth. And you see places we begin to terraform the Earth, you know, the Palm Islands in Dubai. You see how every desert on Earth, we are pumping up fossil water from deep down below to grow these crops. And when we draw down that fossil water where you can't reach it anymore, they just move downstream on the underground river to pump it further up. And so, like in this case, the city that these crops were being created for a city that was way off here that I saw a little later. But you can see how they're dying off. You know, the farms are dying off and they're having to move them further away. And then those die off and they move them further away. And those die off and they move them further away. And you can look at that and go like, this is just not sustainable, right? We're drawing out this reservoir that took tens of thousands of years to fill. And pretty soon there won't be any of that fossil water around. And you see all the fires burning in the Amazon. And you see all the fires burning across Africa. When I grew up, we used to see all the TV commercials about save the rainforest. But the same thing's true happening in Africa as well. Sorry, I got to go back to that slide that was out of order. And it wasn't until I went around the Earth maybe 100 times that I happened to fly over a daylight pass over Austin, Texas. So where Star and I have lived for decades, and you know, an area that you know, I've known very well. I mean, I've driven it from there to Houston to Dallas to the Galveston beaches through my whole life. I've hiked and camped and biked these areas, so I mean, I get it. I know the sense of the scale of this part of the Earth really well, and I've just been around the whole Earth about 100 times, kind of watching it very intently, and so you suddenly have this epiphany where you go, I now know the true scale of the Earth by direct observation. And when that thought crosses your mind, you have an incredibly powerful physical reaction, where it feels like, you know, in the movies where they will, a scary movie in particular, they'll have an actor in a hallway and they'll dolly a camera back but zoom the lens in, where the actor stays the same size but the hallway kind of collapses around them. Well, when you're looking out the world at this moment, of course the Earth doesn't change size out the window, but your conception of the scale of the Earth just goes zhunk. And it goes from being amorphously large to, you know, finite and small. And it's a very powerful moment. And as soon as I had that reaction, I'm going, that can't just be me that's had this moment. And I'd never heard the word overview effect prior to my flight, but as soon as I got home and Googled it, it's a pretty common experience for people who fly to orbit. And seeing all those things like the fossil water issues, you know, and you know, so you know, it just kind of becomes acute to you that, you know, how easy we can pollute the tiny atmosphere we have, how much we are drawing down fresh water basically everywhere, how much we are consuming the natural vegetative productivity of the surface of the Earth at pretty close to its natural capability to produce. And a lot of those could be fixed by, for example, desalinating water to get more fresh water. But of course, that takes an amazing amount of energy, which is actually, in fact, the number one problem we have is global energy supplies, which also causes things like global warming. And you know, so you just sort of get this deep sense of how all these things interrelate to each other that you wouldn't have had before. And even though I would have, probably described myself as an environmentalist before I ever went, I've feel much more passionately about it since my flight than I did before. Sadly, though, it eventually becomes time to go. I undocked and went with the two guys that would not be in my movie to return to the Earth. While it took us 2 days to dock, you get to the ground within 5 hours of undocking. And in fact, most of that time is just spent drifting away from the satellite. When you're docked when you're latched onto the space station, there's actually a couple of springs or a few springs under compression, so that when you unlatch, those springs push you away, and you actually just coast away under that tiny impulse of the spring for a couple of hours. And you do that because you don't want to power up the engines and spray fuel on the space station itself. And so you just hang out and drift away for a while. And then once you're away, you only have to burn the engines and slow down a tiny bit, because you better be going 17,210 miles an hour or you will not remain in orbit. So you slow down just by a handful of miles an hour, 100 miles an hour or so, and then you begin to fall back into the Earth. And when you fall in and you hit the upper atmosphere, you're still traveling basically 17,000 miles an hour. And so that is fast enough that you are ripping molecules apart. So you're literally tearing atoms into their constituent parts just by physical brute force. And that turns out to be enough force that you are creating a plasma that is hotter than the surface of the sun. And my shoulder is literally touching this window, and it's got 3 or 4 panes of glass and quartz and a few other clear materials. But so within 6 inches of my shoulder, it is hotter than the surface of the sun. And it's just intellectually interesting to realize, how close you are to, ultimate doom, and how it wouldn't take things to go very wrong at all before it would go really wrong in a hurry. And but on the inside, it's actually shockingly comfortable. It turns out because of the teardrop shape, it creates a little vacuum jacket around the spacecraft. So in fact, even those windows aren't getting particularly hot. They're getting a little bit of char on them from debris that they blacken over time, and the outer paint is eventually popped off before you hit the ground. We had some malfunctions when the parachutes deployed. Had this big bottle thing come jam between my seat and the window, and my shoulder caused some trouble. We also had some smoke come pouring into the cabin during reentry, which was exciting. But eventually, a parachute deploys, which is sort of the only thing that really better go right in a capsule is to get the parachute out. Otherwise, you could literally turn off the power and it would all generally be just fine. But you do want that parachute to deploy. And unlike U.S. capsules, which often land in the water, these land on land. And so even with that big parachute, you're in a 6-ton vehicle that hits the ground going 30, 40 miles an hour. And so when you hit the ground, it is a wallop. And you, in fact, then bounce and roll in this 6-ton vehicle. So it's shocking. But it's survivable. And you pop out, and my dad was there to help pull me out. He actually helped me board the vehicle around my mission control team, so it was actually great father-son bonding time for my Spock-like father, who otherwise is emotionally detached. But now let me take you over to why, so my wife would say squandered. I squandered the majority of my net worth to make that trip. I mean, I really did. So I could not go back. Even if I do want to go back, I will not go back under anything like those conditions. There's no way I could not afford it. The good news is that I believe I will go back. Probably not for 10 or 20 years, but I believe I will. And the reason is because of this new commercialization process. The price is now coming down really fast. And the floor price is a lot cheaper than most people would likely suspect. You remember I said it was expensive and dangerous, therefore uncommon. But if you look at every other form of transportation, cars, boats, planes, and trains, they all have about the same calculus for cost. And that calculus is that however much money you put in the fuel tank, it costs you about 3 times that much to pay for depreciation of the vehicle, maintenance, and insurance. So every time you put $100 worth of gas in your car, it's another $300 for paying for all the rest of it. And that's true for all those. And the main reason is that for all those vehicles, once you run out of gas, you go to the gas station and you put in some more gas, and then you continue. Whereas for rockets, in the past, you launch it once on its maiden voyage, you drop off its stages to crash into the ground somewhere, and then when the capsule returns, it also smacks into the ground at 30, 40 miles an hour. You're not going to refly that sucker. And even though in theory the shuttle was reusable, the practical reality is they had to take off basically all the tiles, put back on all the tiles. They had to refurbish all the solid rocket boosters. They were dumped into the ocean. They had to be desalinated. It is highly debatable as to whether that really saved much money, even though that was the intention. But that's what's really changing, is we now have people like SpaceX who are saying, it's supposed to drop in our boosters somewhere. Let's go land them. And just this thing, that first stage, which now they're getting better and better about relanding. If you wanted to buy a SpaceX launch yourself, I think they charge about $65 million today is the price if you want to buy the whole rocket. Do whatever you want with it. Go wherever you want, take 6 people with you. Still not cheap, but that takes, just reusing that, cuts $40 million off the cost, landing that right there. And so 40 out of 65 million is a pretty big discount with a simple piece of technology. You got it. We're all going. Let's all go together. We just got all crammed into a pretty small space. And but also Elon is planning to land his boosters. He's actually saying, the capsule. Most capsules have an escape tower that is jettisoned and thrown away every cycle. And he's saying, why throw it away? Why not keep it with you, and instead of deploying a parachute, use it to land? And that way you land soft, and you're not throwing away the fuel that you would otherwise use for the escape tower. With those changes, he thinks he can take it down from $100 million per astronaut to $1 million per astronaut. That is 100 times cheaper. And you might go, okay, most of us don't have $1 million in our pocket, but that's still a hell of a lot better than it was, right? And what's interesting is that's still not the floor. The floor actually is there's a whole other kind of propulsion, which somebody was talking to me about my wife's rocket stuff. This is actually something she's working on. So it turns out one of the reasons that rockets are so expensive is, if you take a rocket and a cargo-containing ship, if you were to take as big a drill as you wanted to and drill holes above the waterline in a cargo vessel, it would still work, right? It's probably not going to sink. Frankly, you could put a few holes below the waterline and it probably wouldn't sink. You know what I mean? And it's definitely not going to break up and blow up. On the other hand, if you did that same experiment with a rocket, it would blow up and or fail during its launch. And that's because 95% of the mass of a rocket is the fuel and oxidizer. They have no mass left over for making it strong and therefore robust. And that's really because you have to carry your energy with you. And so if you can just not carry the energy with you, it completely changes the calculus. And so what my wife's doing, I'll skip one slide here, is she's doing this. They're taking electricity from the electrical grid, storing it in a giant battery pack, dumping that battery pack over 810 seconds, the time it takes to get to orbit, through high-power microwave generators, basically a microwave laser, using big dishes to tune that laser to aim at the belly of a space plane. The belly of the space plane already needs to have a heat shield on it for re-entry, but they're going to heat the heat shield during ascent. And the reason they do that is, as opposed to carrying fuel and oxidizer, they bring a little bit of a propellant. You still have to have something to shoot out the back, some Newtonian stuff, some particles, burp out the back. But they do it by flowing that through the heat shield. And so the heat shield's being cooled by a propellant going through it. It's expanding because the microwave heating it. That is ejected out the back. Your energy you can put in is unlimited. The more of these lasers you put on the ground, the more of these microwave sources you put on the ground, the more energy you get. And so you can actually reverse that calculation of mass. You can take a lot more cargo. You can build a lot more robust vehicle. You can have a few failures in it. It wouldn't crash. It wouldn't blow up. It would be more robust for repeated landings. And then this is what's happening with the cost. So you go back in time to Saturn V, which is super expensive. You get over here to the Falcon 9 is already super cheap. And but if you do things like electromagnetic propulsion, it can be even 10 times cheaper. And that brings us down to, it's still not cheap. It's still like $100,000 per person. But 100 grand, if you thought 100 million was out of reach, we're not talking about 1,000 times cheaper. And now you really are in the basis of you could consider it. Now, at $100,000 or $1 million a seat, it's still not going to be a great vacation destination because it's still a buttload of money. But it's interesting to note that, like some of my partners in these other exploration companies, like if you wanted to go climb Mount Everest, which obviously a lot of people do, it's between $70,000 and $150,000 for you to go. And so there's already a lot of people on Earth that climb it. There's hundreds every year that go climb Mount Everest. So there's probably hundreds every year that will go to space, even once you get it down to that kind of price point. But more importantly, this is what's happening. With my own flight, I paid some tens of millions to go, but I earned back a reasonable number of ones of millions. I still lost a lot of money, but I didn't, but I made a dent in it at least with all that commercial work that I was talking about. Well, if Elon's even close to being right, and he can get the price down to 1, 2, 3, 4 million, I would have been profitable on my own flight. And if I can make money taking myself to space, that's when I'm going to say, hey guys, I need to be able to operate the robots from the space station, and I'll hopefully go back. But that's also where I'll bet a lot of you would do the same thing. If you can get paid to go be a wrench-turning monkey in space, why wouldn't? Of course you'd go, right? Now, that still doesn't mean there's not going to be competition as to who's, the most qualified. But the point is now an even playing field. It's now one of these things where, if you or your kids want to go, like, I really want to go do this, and, it's a completely reasonable thing to consider as a future for yourselves and especially any of our kids. And so here's what I think is going to happen. So we already have all these suborbital vehicles coming into existence. And these are not particularly scientifically or commercially useful other than for tourism. And in fact, you're still going to be paying a pretty good price for these. It's still going to cost $50,000 to $250,000 to go take a suborbital trip. I'm pretty excited about going space diving once we get these things going. We already have now a bunch of commercial vehicles that are going to be operating in orbit. Not just NASA's Orion, but Boeing and the Dragon and the Sierra Dream Chaser. Not only is SpaceX doing man-rated boosters, but the Atlas and Delta and all these others that we've had launching satellites are now being human-rated. So there's now competition that's bringing these prices down, and these people are all now starting to look at reusability also, so their rocket prices start coming down. When I went up onto the ISS, for me to use anything up there cost $1 bazillion because Congress mandated that if I wanted an ice cube, for example, I had to pay my fair share of the launch cost of the water and the energy and the TDRS satellite network to communicate about it. And so basically to do anything would have cost hundreds of thousands of dollars to do something inanely silly. So I didn't do much with NASA. I did all my stuff independently. But now the United States has converted into a national laboratory where if you can get there, it's free, which makes it a lot easier. We have also people like Bigelow and others who are now putting private modules in space. There's private property being attached to the space station right now. And that's going to increase. And so even in 5 years or 10 years when the governments give up on the space station, these guys all plan to just dump the government parts and have it all private. And so again, the cost will come down even further. And then there's things like I was doing with protein crystal growth. There's people doing vaccine development that I think will be commercially viable in space. You even think of the really expensive things, the things that are really important, like satellite communications, we do at very high cost because it's worth that very high cost. But now we're able to do things at much lower cost, doing constellations of small satellites in low Earth orbit versus these big geosynchronous things, farther out. And that begins to open the door for things like space-based solar power, which is one of the topics I could talk about. Asteroid mining, which we talked a little bit about a couple nights ago. What's interesting about asteroids is, and we sort of talked about this the other night too, is just how there's tons of asteroids orbiting really close to the Earth, even around Lagrange points and things of this nature. And some of those will most assuredly be made out of platinum or water, or things that would be very valuable and useful, so pretty easy to go pick up. And also, of course, we need to be thinking about planetary defense. Just as soon as in 2029, there's an asteroid called Apophis that is going to pass shockingly close to the Earth. So close to the Earth's gravity will bend its trajectory dramatically, as you can see. And about 10 years after that, it's coming back again because of this encounter, much closer. And so, sorry? No, we're going to Mars. And so, and it used to be, it's interesting when I've been for 8 years since my flight, I've been talking a lot about space. And I used to say that, Mars is still probably 20, 30 years out. I actually now believe Mars is within a decade. And the important part about that is that when things are more than a decade out, it's politically impossible to get them funded. Because, if you think about even Bush 1 or 2, announced plans to go to Mars over 30 years, but he didn't fund it. And Obama didn't fund it. And the reason why they didn't fund it is they're going, it's 30 years away. I'm going to pay the political price for funding it. And I'm definitely not going to get you the credit. And not only that, there's probably going to be an economic up or down between me and 30 years from now, and somebody's going to stop. And so it's unsafe for me to stop it and assume that 30 years from now we'll actually get there, so why start? But once it's within a decade, some new president, like one coming up, could say, I'm going to start it, and if it doesn't quite finish in my time, my immediate successor could finish it. And therefore, they probably will. If there's only 20% of the time left, they'll probably finish it and get a lot of credit for it. And that's exactly what happened with the moon. And so I actually think we're now within 10 years of Mars, and I only have thought that for 6 months. And so I think it's time to kind of go do it. And in fact, there's an old slide. This one says 30 years. I hadn't updated that slide. But I also believe we really, we ought to go. I think I mentioned to some of you yesterday that I got Stephen Hawking to agree to do a quote on the back of my book, and this is why he agreed. I took him on a zero-G flight some years ago, and he of course believes we should also be multiplanetary just to save us from extinction, which it will come eventually. I mean, the sun will die eventually, but even before that, there's probably many other things that will threaten us. So no time like the present to get started. But anyway, that's it. That's my case as to why I think if you want to go, you can go.